Hi guys, welcome back. And we have our next speaker here. He's part of the Android platform team at Tinder. He's passionate about writing code and create clean code and writing and creating great user experiences on mobile and web. His talk is going to be about taming WebSocket with Scarlet. And this is Zhixuan Lei.
Hello. Hi, everyone. Thanks for coming. My name is Zhixuan. I'm a software developer at Tinder. Our headquarters is in Los Angeles, and we have an office in San Francisco. So if you want to work in sunny California, please talk to me after the talk. And before I start my talk, how about we have some fun, everybody? Raise your hand if you love superhero movies. Yeah. Raise your hand if you don't know who she is. Great. She is Scarlett Johansson, the Black Widow from the Avengers. We're not going to watch superhero movies today. However, I'm going to show you something just as awesome. We're going to talk about Scarlet, a library that we created at Tinder that makes WebSocket on Android as simple as 10 lines of code. Has anyone used WebSocket before? So WebSocket is a communication protocol for real-time applications. It creates a persistent connection between the client and server. Just like a phone call, it's bidirectional. Our app can talk to the server. The server can also talk to our app. Let's see it in action. Here's how you will create a WebSocket connection in JavaScript. You can listen to when the connection is open and send a message to the server. You can also listen to messages from the server and process them. Uh, that's cool, right? But what's the big deal? WebSocket is not the only way our app talks to the server, and most of our apps already use REST. Why should we even care about WebSocket? To answer this question, let's use an airline analogy. Raise your hand if you arrive at Oslo by air. Yeah. Was your flight on time? Mine was not. Imagine that you arrive at the airport and your flight is delayed. What do? I would do my best to keep myself up to date with the flight status. My favorite tool for checking flight status is Google. Let's do a quick Google search of my flight number. So according to Google, my flight is 42 minutes late. Essentially, I just made a REST request to Google to check my flight status. Let's wait for 10 seconds and see what happens. So 10 seconds later, the browser still says 42 minutes late. Because we have waited more than 10 seconds, the data on my phone is likely to be out of date. Let's refresh and see to get the latest status. And oh, my flight status has changed, and my flight is now 1.5 hours late. Look how inconvenient this experience is. In order to stay up to date with my flight status, I have to manually refresh again and again. Wouldn't it be great if I can subscribe to my subscribe flight status with the airline, and they can send me a message whenever my flight status changes, and it can be a message via text message like this. When I registered my phone number with the airline, I established a persistent connection using the cellular network. The airline can send me flight status updates as it happens. Compared to checking flight status on Google using REST request, this is just like you having a WebSocket connection with the airline where flight statuses are sent to you. Essentially, the difference between REST and WebSocket is pull versus push. And let's take a look at this comparison diagram. On the left, we have long polling, where the client has to ask the server again and again for updates. It's easy to implement, but it's expensive and has a longer latency. In this diagram, we made a total of 4 round trips to the server. This involves unnecessary overhead because HTTP requests and response usually contain more data than necessary, such as a long list of headers. In addition, polling is not real time because the latency is limited by your polling frequency. So if you make a request every 2 seconds, you could experience a 2-second delay. Polling is also it could also be wasteful. In this diagram, we receive 3 duplicate responses before the data on the server changes. This could have been avoided if we use a push model. As we can see on the right side, WebSocket uses a push model where you can subscribe to the server and messages will be sent to you. Compared to long polling, the push model is a more efficient way to build real-time applications. WebSocket is useful in many apps. For example, chat, where you want to receive incoming messages in real time. And this is what we use WebSocket for at Tinder. And you can use it for real-time location sharing, online games, and apps that show real-time price. So WebSocket is powerful. However, it has a big problem. WebSocket is not easy to maintain on Android. There isn't a good WebSocket library that can help you avoid boilerplate code and spaghetti code. Boilerplate code is a lot of code that does minimal jobs. It adds complexity to your development and just make your code base more difficult to maintain. Let me show you why we don't want to deal with boilerplate code. So over the years, the Android community has built many great libraries that makes Android development easy. HTTP is easy. With Retrofit, it takes just 10 lines of code to build a HTTP client. Persistence is easy. With Room, it takes 40 lines of code to set up a SQLite database. WebSocket should also be easy, right? But it's not. It takes 500 lines of code just to set up the WebSocket connection. This is because the existing WebSocket libraries are low level and verbose. So WebSocket is not easy to set up because you have to write a lot of boilerplate code. But even if you are joining a project where WebSocket is already set up and boilerplate code is already written for you, you still need to deal with spaghetti code. Spaghetti code refers to unstructured and difficult to maintain source code, and it's unmaintainable. And what makes WebSocket on Android prone to spaghetti code? It's because state management is complicated and we need to deal with a lot of asynchronous events. As programmers, we tend to focus on the happy path and overlook the error case. WebSocket is straightforward when the connection is open, but things can get complicated when you need to recover from a network failure. So WebSocket can fail for many reasons. It may fail when you're on a train going through a tunnel. It may fail when the server is out of memory and tries to release resources. It may fail when your app is killed by the system. Let's take a look at the happy path. On this diagram, the horizontal axis is time and the vertical axis indicates the connection state that we want in our app. When at 0 second, the server is online, but the user is not in the app. So we don't want the connection to be open. And after right now, the user just opened the app and we want to connect to the server and the connection is on. Okay, the user is still in the app, so we want to keep the connection on. But when the user leaves the app, we want to turn off the connection. This is simple and straightforward. What should we do when the connection fails? Let's take a look at an error case. So connection is on, and the server, however, crashes at the 4th second, and the client, what the client should do is it should retry until the server is back online. This is actually very complicated because it involves connection. Our app will need to react to connection state changes and the application lifecycle. And when the state management is complicated, it takes a lot of effort to write modular code that is easy, that is readable. Scarlet is here to help. Scarlet is the first WebSocket library that minimizes boilerplate code and spaghetti code that you need to write. It's declarative, so you only need to declare what your endpoint looks like, and Scarlet will implement it for you. And it reduces boilerplate code to as few as 10 lines of code. As you will see later, this is all you will need to integrate any WebSocket APIs. Scarlet is also modular, meaning that it consists of modular components that can be developed, that can be changed independently. We identified a few key components and created well-defined abstractions for them. We made them into plugins, essentially. WebSocket, which is the first plugin, is an interface that hides specific WebSocket implementations from Scarlet. It enables Scarlet to work with any WebSocket implementations, or any WebSocket libraries that you prefer. The second plugin, Message Adapter, encapsulates the serialization and deserialization of messages. And Stream Adapters encapsulates the conversion between different asynchronous abstractions. I will explain each of them later. Let me first show you why they made Scarlet modular. What's the most popular WebSocket library on Android? Does anyone know? Yeah, I think so. I think it's OK HTTP. And for parsing JSON, I prefer using Moshi. And I would like to use ArcsJava to handle message asynchronously. We made a plugin for each of these libraries, and we made a few more. Because Scarlet is modular, no matter which library you prefer, you can use it with Scarlet. In addition to those plugins, we also have two state management plugins. Scarlet uses lifecycle and backup strategy to keep the connection open for you. A lifecycle declares when the app should connect to the server. When the lifecycle is on, basically when the user is in the app, and the connection failed, Scarlet uses backup strategy to determine when to retry. These plugins allow Scarlet to take over state management for you so that you don't need to write any spaghetti code. More on this later. Just to recap, Scarlet is declarative and modular, and it makes WebSocket on Android as simple as 10 lines of code. Let's see a real-world example. Let's use Scarlet to add a real-time Bitcoin price to our app. To draw such a graph, we need data points. We call each data point a ticker. A ticker represents the Bitcoin price at a point in time. When we will be using GDAX, which is I guess the most popular cryptocurrency exchange in the US, and we will use it to fetch the latest price for Bitcoin. So what does WebSocket endpoint look like? It's very different from a REST API that we're used to. While a REST call has a request and response, but in a WebSocket connection, we send messages back and forth. According to the documentation from GDAX, after the connection is established, the client should send a subscribe message to the server. After that, the GDAX server will send us tickers in real time. Let's dive right in. Scarlet is similar to Retrofit. It takes an interface and creates an implementation. To send a subscribe message to the server, you will declare a method with the send annotation, and you'll specify with the object you want to send. In this case, it's a message of the subscribed type. And a subscribed message look like this. It has a type, product IDs, and channels. This is specific to GDAX. Because we're interested in the Bitcoin price, we will send a message like this to the server when the connection is established. After we've created an implementation of this interface, we will use this method to send the subscribe message. We have figured out how to send the message, but we haven't figured out how to send it at the right time. In order to listen to when the connection is opened, we need to declare another method with the receive annotation. This method returns a flowable of events. We can subscribe to it and send the message right there. After we send the subscribe message, the server will send us tickers as documented on their website. To observe the tickers, we just need to declare another method with the receive annotation. And this method will return a flowable of tickers, and we can subscribe to it and process the data. Just to recap, we integrated the JDAX WebSocket API by declaring 3 methods in an interface. We used Scarlet to generate an implementation of this interface. After we send a subscribe message to the server, we process the tickers one by one. As promised at the beginning of the talk, we did it in about 10 lines of code. So we have seen how declarative Scarlet is. Let's talk about plugins. These are the plugins we have right now, and these are on the roadmap. Plugins are easy to implement because they are meant to be customizable. If you write your own plugin someday, please share it with us. Let me show you how to use plugins. If you're starting from scratch like we just did, here's the recommended configuration. First, let's create a Scarlet builder and add a WebSocket plugin based on OKHTTP. And we recommend Moshi for serialization. And let's use ArcJava to process the messages. Here we go. And if you're adding Scarlet to an existing project, here's how to configure Scarlet to be compatible with your existing app. Let's start with the WebSocket factory. WebSocket factory is an abstraction that allows Scarlet to support any WebSocket implementation. You can use OKHTTP, which is recommended, or you can use a mock server, which is useful for testing. And you can even write your own. We might support other WebSocket libraries in the future if you are interested. Next, let's talk about message adapters. WebSocket supports text and binary messages. And Scarlet uses message adapters to parse messages, including the subscribe and ticker messages in the previous example. We support Moshi, Zhixuan, Prolabuf, and Jackson. The slide is out. The slide is out of date. Somebody actually created a PR for this adapter, and we might support XML in the future. And stream adapters. The data we receive from the server in a WebSocket connection is a stream, which is a sequence of asynchronous values. Scarlet has a built-in stream type. It uses string adapters to convert the built-in stream type to the the asynchronous libraries that you prefer, such as RxJava. We support RxJava 2, RxJava 1, and Kotlin coroutine. We might support other abstractions such as live data and flow in the future. That's it about plugins. And once set up, you'll be amazed how easy it is to maintain Scarlet. Let's say we want to start receiving level 2s from GDAX. A level 2 provides insight into Bitcoin trading. And guess how many, the data looks like this in JSON. Guess how many lines of code we need to change to support this. We only need 2 lines of code. All we need to do is add in a new method to the interface. Let's look at another example. Suppose we want to use a custom WebSocket implementation, and this only requires a one-line change. All we need to do is change in a plugin. Similarly, switching JSON libraries is also a one-line change, like this. Besides being declarative and modular, Scarlet is also very reliable. As a library sponsor by Tinder, Scarlet is tested at scale in production. We use Scarlet to deliver matches to thousands of devices around the world, and we have been using it for 8 months. We found 0 issues in production. Although state management is complicated on Android, Scarlet is not written in spaghetti code. The state management in Scarlet is clean, is testable, and very debuggable. Scarlet, Scarlet is testable because it's driven by a state machine with immutable states. We actually wrote a Kotlin DSL for writing declarative state machines, which is available as a separate library. Let's take a quick detour to see a simple usage of this DSL. This diagram represents a water state machine. We all know that water has 3 states, and solid, liquid, and gas, and there are 4 possible transitions between these states. Let's model this state machine in Kotlin. We can use a seal class and to represent the states, and a seal class to represent each event that triggers the transition. And let's go ahead and declare a state machine using the state and event. Let's add a initial state, which is solid. And we can, in the solid state, when the water is melted, it becomes liquid. We can add more states, more transitions using this DSL. And yep, that's all you need to write to model the water state machine. It's simple and readable, and it's also testable. And in your unit test, you can assert that the initial state is solid. And when the unmelted event is triggered, we can assert that the state machine has changed to the liquid state. We just saw how declarative and testable a state machine can be. Here's the state machine that Scarlet uses internally. It's simple and elegant, and it's also customizable. For example, you can use the concept of life cycle to define when you should keep the connection open. And you can also use a backoff strategy to configure how often Scarlet should retry when the connection fails. Remember these lifecycle plugins? Uh, they allow state machine. Um, they allow the Scarlet state machine to keep the connection open for you. Just to recap, a state machine has two states: started and stopped. It tells the Scarlet to when to keep the connection open, and when the lifecycle is on and the connection failed, Scarlet will retry until it succeeds. The we have a built-in lifecycle for Android, which describes when the app is in foreground. And you can also write your own lifecycle plugins. Uh, for example, if you want to connect to the server only when the user is logged in, you can write a login lifecycle state. A lifecycle plugin. If you combine both of these lifecycles, Scarlet will only connect to the server when the app is in foreground and when the user is logged in. Let's move on to backoff strategy. When the connection fails, Scarlet uses the backoff strategy to determine when to retry. And we have a few built-in ones, such as linear, exponential, and exponential with jitter, which is the one we use in the Tinder app. And of course, you can write your own strategy. That's it about state management in Scarlet. Let's move on. Since Scarlet was released in June, we received a lot of feedbacks from on GitHub. The most wanted feature is supporting more protocols. We are working on a V2 to address this need. Let's take a look at the plugin Scarlet has. All right, here's what we did. We climbed up the ladder of abstraction. We took the WebSocket plugin and turned it into a plugin. By doing so, we were able to support any persistent connection protocols. In addition to WebSocket, we will support service and event, Socket.io, Stomp, and MQTT. By supporting different protocols is actually very challenging. It's challenging because they're very different. Not every protocol is bidirectional. Um, Service and event, as its name implies, only allows server to send string messages to the client. While WebSocket and service and event have only one channel, other protocols support multiple topics and behaves like message queues. For example, if you are building a chat room app, you can have a new message topic only for incoming messages, and you can have a user count topic that only notifies you when the user joins and or leaves the chat room. Finally, Stomp and MQTT plans do not talk to the server directly. They talk to message brokers, which then forward the messages to the server. As you can see, um, it's we actually made a lot of we actually rewrote half of Scarlet to be able to support all these protocols. And I'm not going to go through any code example on the new version, but I would love to discuss it with you offline if you're interested. The source code is available on this branch, and it has been published to Jetpack, so you can start using it today. As you can see, we now have different artifacts in the new version. If your the documentation uh, is not finished yet, but if please check out the demo app for examples. We added service and events and Socket.io to the demo app. That was a sneak peek to Scarlet v2, and I can't wait to discuss it with you offline. Okay. That's pretty much all I have for this presentation. Just to recap, Scarlet is declarative and demands minimal boilerplate code. It's modular, uh, which makes it easy to get started for beginners, and it's customizable for advanced users as well. And it's reliable because it's powered by a state machine that is fully tested. Finally, Scarlet is evolving. We are adding other protocols to Scarlet in addition to WebSocket. I hope Scarlet can make your life easier. Here's how you can get started today. Thank you. I'm happy to answer any questions.